Hello, in this video we're going to talk about valence bond theory for double bonds and triple bonds and what it means to have delocalized electrons. In this video I have my sister Stephanie.
Hello everyone.
She is my hand model and helper for the models that you'll see here in a minute. Okay, and remember we were talking about different ways to think about molecular bonding. And so Lewis structures were in chapter 7. This is a simple way to think about bonding but doesn't give the detail we want. Now we're talking about valence bond theory, which is that electrons occupy these modified hybrid orbitals that then overlap to form the bonds, and then later will come molecular orbital theory. So we had this picture in the last video that valence bond theory is basically you have these two orbitals that overlap, and that overlap makes the bond. It's pretty simple and straightforward. If you have an electron in each orbital with opposite spins, then they will form this bonding orbital with two electrons in it. Okay, so if we can represent these with something that's maybe a little easier to see, hopefully that'll go better. So here we have some globs of Play-Doh, and each one represents an atom, in this case a hydrogen atom, and the surface that we're seeing here is it encloses the area within which you have a 95 or 99% chance of finding the electron. So we draw these nice pretty colored balls and things, and really it's just the electrons in here somewhere, and buried in the center of these spheres is the nucleus. And so in valence bond theory, really what's happening is these two atomic orbitals are coming together and forming a bond. Okay, so now we're going to extend valence bond theory to what happens in the case of double and triple bonds. And so based on what we talked about last time, if we look at this molecule, ethylene, all right, so the carbon atoms right here, they have three different electron groups bound to them, the double bond and two hydrogens. And so the simple thing here to say is, okay, you have trigonal planar electronic geometry. And so that means 1, 2, 3 groups attached to this carbon. And the same is true for the other carbon. And so that means you'll have sp2 hybridization. Well, what makes the double bond happen? And so the right picture here is that you have a p orbital like this, and that p orbital is still existing, unhybridized. And then the three sp2 hybrid orbitals are present around, and that forms the bonds to the other atoms, the single bonds to the other atoms. And so since this is probably kind of hard to see, let's pull out some Play-Doh and take a look. Okay, so the picture that you just looked at is representing a single carbon atom. So if this is our nucleus, and this is the unhybridized p orbital around the nucleus, it'll look a little something like that. And then now the three separate hybrid orbitals, which remember have this shape like this with the business end, I call it, and then the little other end, these go around like this, around the nucleus, and then there's three of them here. And this is looking at just one carbon atom, and this particular model is going to look like absolute garbage by the time I try to get it done. Sure, okay.
It's modern art.
Yeah, modern art, definitely. So this is what it looks like on a single carbon atom. Remember the carbon was in the middle there. And so now what happens to the orbitals on this carbon atom in order to make this type of hybridization happen? So on the left you have the before picture, where you have 2 electrons in the s and 2 electrons in the p because carbon has 4 valence electrons. And then in the after picture here, well, this carbon needs to make 3 bonds, so there's 3 hybrid orbitals right there. And the hybrid orbitals are all sp2 hybrids because they come from an s and 2 of the p's to make sp2 hybrid orbitals. And there's only 3 of them. Each sp2 hybrid orbital has 1 electron in it. And remember, if this is singly occupied with an electron, it allows it to overlap with another atom and make a bond. But then we have this 1, 2p orbital that's left, and it still gets an electron inside it because this 2p orbital is used to make the double bond. So to show how this works, we're back to our models. So we now built another one where we have this little guy in here is the carbon nucleus hiding in between its unhybridized p orbital, and then the 3 different sp2 hybrid orbitals around the outside. Very nice, very nice. And then this is going to make a number of different bonds in order to make this ethylene molecule. So first, the two of the hybrid orbitals will overlap to form the bond between the one carbon nucleus here, where my finger is, and the other carbon nucleus over here. And so here we go.
Done it, done it, done it.
Perfect, perfect, perfect. All right, so now we have a bond here. So this bond in the middle is called a sigma bond. And I have no idea if this is going to work. Can I draw a sigma on here? Oh, yeah. There we go. So this is called a sigma bond, and this is the Greek letter sigma that I'm trying to draw on here. Okay, and the sigma bonds are basically directly between the two nuclei right here. Okay, so then now all of the other hybrid orbitals will then make bonds to the hydrogen. So with the same suitable sound effects.
Done it, done it, done it.
There we go. So they overlap here and make a bond to these hydrogens. We'll overlap here, make a bond to these hydrogens, and now we're almost there. So we have our sigma bonds between the two carbon nuclei, and then these are also sigma bonds between the carbon nucleus here and the hydrogen nuclei out here. So right now we have 1, 2, 3, 4, 5 sigma bonds in our molecule. And now another thing that happens here is what's called a pi bond. So the unhybridized p orbitals, now we get to use them, is that they overlap sideways like this. Smush.
Smush.
To make what's called a pi bond.
Can we eat it?
Not that kind of pie. Can't eat it. Sorry. There we go. So this is a pi bond. And now a pi bond, just like a p orbital, has two lobes. It has lobes above and below the line that connects the two carbon nuclei. And the electrons, the two electrons in this pi bond can be found either above or below, anywhere in this region. And our Play-Doh's going to fall apart.
No.
Oh.
That's postmodern art.
Postmodern art, yeah, very true. Now, as you can imagine, this is really difficult to represent on paper, how you show these orbitals. So on this slide, we have a number of different ways to try to show that. So, top left, the carbon nuclei are right here. And then each one of these green lobes here, this is one sp2 orbital. Here's another. Here's a third sp2 orbital. And then the little back ends here are not typically shown when you draw these because they tend to clutter things up. But that's just a visual thing, not a scientific thing. And what we did first with the Play-Doh is we took this sp2 hybrid orbital and this sp2 hybrid orbital and we overlapped them to make this one orbital in the middle, which is called a sigma bond. And then we took the other sp2 hybrid orbitals and overlapped them with the hydrogen to form a bond this way, which is also called a sigma bond. So the sigma bonds come from the hybrid orbitals. Now, this picture on the top left doesn't show the p orbitals and how they make the pi bond. The picture on the top right is just showing p orbitals, right? Our carbon is here, carbon is here. Here's a p orbital, a single p orbital with two equal lobes, and then there's another single p orbital on the right side. And then they will overlap sideways like this to form a pi bond. And just like a p orbital, a pi bond has two lobes above and below the nuclei. So outlined in red here is a single pi bond. Then down on the bottom right here, we have a diagram that tries to put it all together. So here's the carbon nuclei again. This is showing the hybrid orbitals that have already overlapped to form the sigma bond in the middle. And then the hybrid orbitals that overlap with the hydrogen 1s orbital to form these sigma bonds out here. There's 5 of them. And then it shows the pi bonds, which came from the p orbital here and the p orbital here. They overlapped on the top and the bottom to make this pi bond. And this above and below represents a single pi bond, even though the pi symbol is written twice. So in this molecule, we have 5 sigma bonds, and we have 1 pi bond. Now let's try to define this a little better. So sigma bonds have electron density between the two nuclei. So the sigma bond between the two carbon atoms the probability of finding the electron lies between the two carbon atoms on the line that connects the two. Sigma bonds are symmetrical about the line that connects the two nuclei, and they come from the hybrid orbitals. Pi bonds have electron density above and below the plane of the nuclei that contains the atoms. And so the electrons are likely to be found above and below the atom. They form the double part of the double bond, if you want to think of it that way. And so when you're making a double bond, it'll consist of a sigma bond and a pi bond together. The geometry doesn't work to be able to put two sigma bonds together to make a double bond, because one of the sigma bonds is already between the nuclei. Where's the other one going to go? They can't take the same space like that. So if you have a double bond, you have a sigma bond and a pi bond. Now what about if you have a triple bond? So say you had N2, the molecular nitrogen. So if you looked at each one of these nitrogen atoms, this nitrogen has one thing attached to it over here, the triple bond, and another thing attached to it here, the lone pair. So that means since there's two things attached to it, it has linear geometry. We call this sp hybridization. And now, all right, when you make sp hybrid orbitals, you take from the before picture on the left, you take an s and a p, and you merge them together to form these hybrid orbitals, the two sp. You take linear combinations of them to make the two sp. And so there's two of these sp hybrid orbitals, and the principal quantum number is 2. So you have two sp orbitals. Okay. Now, you also have two unhybridized 2p orbitals left over. That's totally fine. Now, the electrons here, you have 5 electrons total, and if you're just filling this, you might think you put 1, 2, 3, 4 into the lower orbitals, and then you'd just have 1 in the higher energy orbitals, the unhybridized p orbitals. And that would make sense if this was an isolated atom. But since this is not isolated atom, that's not favorable. What's in fact more favorable is to do the electrons this way so that then you can make bonds. Because remember, making a bond is a very favorable thing to do. And so this is overall better, even though we have an electron at a higher energy level than we would otherwise. So we have a pair down here in the hybrid orbitals. And hey, remember, when you have a pair in your hybrid orbital sets, that means you have a lone pair. So this represents the lone pair. This electron here represents the sigma bond that's in the plane between the two nuclei. And then these electrons here will both make pi bonds by overlapping sideways. And you can think of it as one of them makes one of the triple bonds, the other one makes the other one. I don't know, it's kind of a memory trick in any way. So ultimately, this is going to make your sigma bond, and this is going to make 2 separate pi bonds. So again, this is kind of hard to show. Let's do the Play-Doh. That's just going to be better. Okay, so let's put together the nitrogen atom. So we have our nucleus represented by the rock. We have 2 unhybridized p orbitals, and then we have the hybrid sp. Here's one of them, here's the other one. So let's put it together. So you take your nucleus, and then you have the p orbital with the nucleus in the center, smush. And then you have the other p orbital 90 degrees from that, smush. And then you'll have the sp hybrids, smush, smush. Maybe that's better than the computer, who knows? So we have this, remember the nucleus in the center, our 2 p orbitals, our 2 hybrid orbitals. All right, let's make another one.
Like magic, we have 2 of them now.
All right, so when we make the bond between one nitrogen nucleus and the other nitrogen nucleus, the hybrid orbitals overlap to make our sigma bond in the middle. And then the unhybridized p orbitals overlap. We're going to do the front and the back first. So these ones overlap this way to make, oh no! To make one pi bond. And then the other ones overlap this way to make the other pi bond. And so you have what looks like a very weird hot dog, where in the middle there's a sigma bond, And then on the outside, there's two pi bonds. Here's one, top and bottom, and then here's another one, front and back. So two pi bonds and a sigma bond make up a triple bond. And then these hybrid orbitals on the outside here, they will hold the lone pair. Or if this were to bond to another atom, it would come in right here. But that's not the case we have. We have a lone pair in these hybrid orbitals pointing towards the outside. Okay, and then now to show what this looks like on the picture. So again, the nitrogen nuclei are here. And each nitrogen nucleus starts with an sp hybrid orbital on the left and an sp hybrid orbital on the right. And then those sp hybrid orbitals in the middle overlap to make a sigma bond. And remember, for this to work, each one of these sp orbitals needs to have a single electron in it. And then when they overlap, they make a bond that has two electrons. And so that's why, in the previous slide, on a single nitrogen atom, you needed an sp hybrid orbital that had a lone electron in it, because that's the one that's used for the bond. Okay, back to the picture. So then on the left here is trying to show a single nitrogen atom with the two p orbitals and the two sp orbitals. And then the picture on the bottom right is trying to show, okay, this p orbital will overlap with this p orbital and make a triple bond kind of this way, up and down on the screen. And then this p orbital that comes in and out of the screen will overlap in front and behind to make another bond, another pi bond that's part of this triple bond. So to review, a single bond consists of one sigma bond. If anything, maybe sigma and single, maybe that word being similar to each other, maybe that helps. So a single bond consists of a sigma bond. And in this little picture over here, there's a nucleus right here and a nucleus right there. And this was one hybrid orbital to start with. This was another hybrid orbital to start with. And now it makes this sigma bond. Now a double bond consists of a sigma bond and a pi bond. So this picture on the right is showing just the pi bond. So this carbon had a hybrid orbital like this and a hybrid orbital like that. Then they overlap to make a sigma bond in the middle. And then the pi bond came from the p orbitals on this carbon that now above and below this plane that has the other atoms in it is where the pi bond sits. And also not shown on here is the hybrid orbitals coming this way out of the carbon and the overlapping with the hydrogen 1s orbital in order to make the bonds there. Really hard to show on a flat screen. Now a triple bond consists of the sigma bond in the middle, and on this crazy hot dog-like picture, the sigma bond is in purple kind of down the middle here. And then it'll have two pi bonds. Here's one above and below, and then the other one will come in and out of the page towards you here, and then this one back here. Now, we draw the pi bond like this because we think of it coming from individual p orbitals, but in reality, the pi bond in a triple bond is actually more cylindrical. That doesn't really matter because it's a linear geometry anyways, whether this is cylindrical or not. But just kind of a nuance, if you will. Okay, so for example, let's describe the bonding in the formaldehyde molecule. Here's the Lewis structure on the right for formaldehyde. So if you look at the carbon, it has three things attached to it, which make it a trigonal planar geometry. And then that means it'll be sp2 hybridized. And so you have three sp2 orbitals. Here's one, here's another, and here's the third. And on the oxygen, it's also sp2 hybridized because it has this bond here, and it has two lone pairs it needs to hold. And so that's sp2 hybridized. So here's 1, 2, 3. Now the hybrid orbitals that point towards each other overlap and form this sigma bond here in the middle. Now the hybrid orbitals pointing towards the hydrogen overlap with the hydrogen 1s orbital and form a sigma bond this way and a sigma bond that way. Finally, the p orbitals on the carbon atom used to sit here. The unhybridized p orbital on the oxygen used to sit here. And then these will overlap sideways like this to form a pi bond that has two lobes, one above and one below. So the simple thing we can ask you about this is how many sigma bonds and how many pi bonds are in this molecule. And if faced with that kind of question, you can just count. Every bond has a sigma bond inside of it. So here's one sigma bond, here's another, and then one of these bonds in the double bond will be a sigma bond. And then when counting pi bonds, well, the other bond in the double bond is a pi bond. So this molecule would have 3 sigma bonds and then 1 pi bond. And you don't need to show the pretty picture in order to figure this out. You can just do it from the Lewis structure if you need to. So I'll do this one as the pop-up question. How many sigma and pi bonds are in vinegar, which is acetic acid? So here's the Lewis structure of the molecule, and answer the question. Okay, so the really important outcome of this is bond rotation. Because this affects geometry, it affects what kind of isomers you can have. This is something we really need to talk about. And now we have the tools to be able to talk about it. So atoms can rotate around a single bond. So in this picture here, we've got ethane, and not very visible, the carbon nuclei is right here, and here's another carbon nucleus right in here. And in between the two carbon nuclei, you'll have these hybrid orbitals that overlap and form a sigma bond in the middle. That got messy. So you have your sigma bond in the middle here. And this sigma bond is symmetric on the line that connects the two nuclei. So that means it can rotate. So just hanging out this molecule, these hydrogens will rotate. And these hydrogens will rotate some direction too. And each one of these will look like little propellers spinning around, even if the carbons are perfectly stationary. So around a single bond, atoms can rotate. And that's why if you have this molecule here, where you have 2 chlorine atoms on a carbon-carbon bond with the hydrogen atoms around, if you draw it on the left like that, and you draw it on the right like this is still the same molecule. You cannot have cis and trans isomers here, because this chlorine atom and the hydrogen atoms, they'll rotate really quickly around and around and around. And so these two molecules that we just drew are in fact the exact same molecule. So you cannot describe them as cis and trans isomers because this is just rotating around. So the chlorine that's here will be here, it'll move over to here, it'll move up here. So you can't describe this as different. It's just you're showing it snapshots of it in different states of its rotation, but that's still the same molecule. However, if you have a double bond, now a double bond has this pi bond above and below the plane of the atoms. And so this pi bond, well, if you were to try to rotate around it, you'd have to break the bond back into its constituent p orbitals, and that costs energy to break a chemical bond. And so while you will see these things break and reform, it does require an input of energy that's higher than what's normally accessible to this atom by virtue of just being in the environment. And so you won't see this bond break just willy-nilly. So that means if you were to draw something trans across a double bond versus cis across a double bond, then you have different molecules because it will not rotate to interconvert from one to the other. So if you go back and look at the worksheet where we were talking about cis versus trans, whenever we have them on a molecule that looks like this, there's a double bond in the middle because that will allow cis and trans isomers because it will not rotate around that bond. Now you can rotate around a triple bond because the 4 lobes of the 2 pi bonds ultimately merge together to be cylindrically symmetric. But the outcome here really doesn't matter because if you can rotate around this bond versus if you can't rotate around this bond, you still have a linear geometry, and so rotation doesn't really affect anything. So ultimately, it doesn't matter whether you can rotate around a triple bond or not. So this limited rotation around a double bond has huge implications all through chemistry and biology. You see because of this. So you have in this molecule called retinal, which is in the retina of your eye and it helps you see, you have a double bond in here. And if that double bond is cis, then this molecule has one shape. And if this double bond is trans, then this molecule will have another shape. And this molecule it absorbs light. And so when it absorbs light, this cis bond will convert into the trans bond, and now you have a molecule of a different shape, which then goes and signals to your body that it absorbed light in this particular spot. And then eventually it'll convert back to the cis form and it'll be ready to go again. And so the energy in this change is about that of some number of photons. And so without the light hitting your eye, this molecule doesn't change shape and your eye doesn't register that light has hit it. So this double bond rotation thing is really big. Okay, another type of question we can ask is how many atoms lie in the same plane of a molecule? I like this question because it makes you think about geometry across a larger scale, and it also makes you think about rotations around bonds. So in order to answer this though, you've got to really think about the structure. So what I have drawn here is ethylbenzene in the organic chemistry form. So now let me redraw it into the general chemistry version. Hold on a second. All right, here it is. So now you have to go around and look at this and think, what is the geometry on each of these atoms that makes more than one bond? So I'm just going to pick a carbon atom in the ring down here and start there. So each one of these carbon atoms in the ring, it has a double bond to one side, and then it has a single bond to two of the other sides. And so this has 3 electron groups around this central carbon atom. Think back to your geometry. That's trigonal planar. Okay, and then you can look at the other carbon atoms around this ring and see that they're all in the same boat. For example, this carbon atom here, it has 1, 2, 3 electron groups. That makes it trigonal planar. Okay, now when you go up into the ethyl part of ethylbenzene, up here, now each one of these carbon atoms is bound to 1, 2, 3, 4 other things. So that makes these both tetrahedral. Okay? So if you think about the geometries, trigonal planar is just that, planar. And so the fact that this is in a plane, well, that overlaps with this plane here, which then overlaps with this plane over here. And you can go all the way around the ring, and since these planes overlap, and critically you cannot rotate around this double bond, that means that this entire ring is going to be planar. And indeed, that's one of the features of this benzene ring, it's called, where you have 6 carbons with alternating double bonds, is that it's planar. So if you work your way around this ring, you'll see that all of these atoms are all in the same plane. Now we just have to think, how far up this ethyl chain does this go? Well, this carbon atom right here at the top of the ring, here's its trigonal plane, like that. Now, so that means this carbon at the top right here is going to be in the same plane as the whole ring. So we know we can at least extend our ring to go around this carbon atom like that. Well, what about these hydrogens and this other carbon up here, right? Is that in the same plane? Well, now you have to think about bond rotation. So you cannot rotate around those double bonds, but you can rotate around this single bond right here. So because you can rotate around this single bond, that means that anything attached to this carbon right here, anything attached to that is going to rotate. So this whole group here winds up rotating around and around, like you're whipping it around above your head in a way. And then these hydrogen atoms here do the same thing. They rotate around this carbon. This hydrogen atom rotates around the carbon too. So you can't say that these hydrogen atoms are in the same plane. So what we have circled now are all in the same plane. So then if you count them up, you get 12 atoms that are in the same plane. So the last thing we have in this video is to talk about delocalized molecular orbitals. And so in this benzene structure we just had, you may have thought, well, it needs resonance structures, which it really does. And so on the right down here, I have benzene shown with both its resonance structures. So I don't know if you remember, but when we talked about why we need resonance structures, it's because it was to fix a failing in Lewis theory or Lewis structures that don't show delocalized electrons very well. So what we did is we just drew both structures with the double bonds in one spot and the double bonds in the other spot and said, look, it's an average of both. So now that we know more about how double bonds work, we can realize what's really going on. So there's always sigma bonds in between the nuclei, and these electrons don't move. They're just held in the sigma bond directly between the carbon nuclei. Here's one, here's the other. They're held right in between the two. However, the pi bonds are the ones that move. And so you'll have a pi bond here and here, here on the top, and then your pi bonds move here, here, and here. It's not the sigma bonds that move, it's the pi bonds, and you'll see why on the next slide. But so we say that the pi electrons are delocalized. They're not just sitting in one spot, they can move all around the molecule. Now, once we get to talking about molecular orbitals, we'll see that what's best to describe benzene here is we use the valence bond model to talk about the sigma local electrons, and then the molecular orbital model to talk about pi electrons. But we're not there yet, so let's just use what we know to talk about this. So again, the sigma bonds are the hybrid orbitals. I mean, they're from the hybrid orbitals, and they're the localized electrons that don't move. So for instance, between these two carbon atoms, there's a sigma bond right here with 2 electrons in it, and those electrons are kind of stuck between those carbon atoms in this ring. Whereas each of these carbon atoms has a p orbital that's unhybridized, and then that p orbital overlaps sideways to form these pi bonds. And okay, based on a non-resonant view of this, you might have these two back here overlapping, you might have these two here overlapping, and these ones here overlapping. But since we know that this really resonates, what that means is that these electrons are delocalized and they can run all the way around this ring, like kind of in a racetrack, but they're waves. So, electrons are waves, you can't really think of them that way. But the electrons are free to roam around this entire structure, both above and below the plane of the benzene ring. Then there's 6 electrons that are running around this structure because there's 2 electrons in each of these pi bonds, and then there's 3 pi bonds. And you really see effects of this in a number of different places in chemistry, that these electrons are delocalized. And so we also see this in, for example, a molecule like nitrite here, where if you draw the Lewis structure of this, you have a double bond that you need to show resonance for. Well, what this really represents is that these 2 electrons in the double bond are delocalized and they can be spread across the whole molecule. And so sometimes you'll see this represented as the molecule with a dashed line present across both bonds to show that these pi electrons are delocalized across the whole molecule. And that's why the bond lengths of each of these NO bonds is the same. It's because these electrons are just kind of spread across all of it. All right, that's what we have. Thanks for hanging in there through a long video. And now you know about how valence bond theory describes double and triple bonds.